Welcome to UTC AI Studio, AI-powered, creativity fueled. Have you ever stopped to think about how your phone unlocks just by looking at you? Or how can some cars just drive themselves? Well, the magic behind all of that is a field of AI called computer vision. And today we're going to dive in and break down exactly how we're teaching machines to actually see and understand our world. Okay, so to really wrap our heads around what computer vision is, let's start with a problem that seems pretty simple for us humans, but is, incredibly complex for a machine. Just think about it for a second. A self-driving car is dealing with this constant chaotic flood of visual information, and it has to process it all in real time. It needs to spot the lane markers, read traffic signs, and tell the difference between a person, a bike, and maybe a fire hydrant. So, how in the world does a machine do all of that? Well, the answer is computer vision. So what is it really? At its core, computer vision is all about giving computers a high-level understanding of what's in an image or a video. We're going way beyond just capturing pixels here. We are teaching machines to pull out meaningful information from that visual data pretty much the same way our own brains do. You see, at the end of the day, the goal here is to copy one of our most powerful senses, our sight, and also the incredible brain power that goes along with it. When we look at the world, we don't just see colors and shapes, right? We understand the context, we make judgments, we make decisions. That is the amazing ability we're trying to give to machines. So how does this learning process actually work? To really understand how this works, let's switch to a powerful example from medicine where computer vision is already saving lives by spotting pneumonia on chest x-rays. The whole thing really boils down to this four-stage pipeline. First, you've got to gather the raw materials, the data, then you prepare it and clean it up. After that, the real fun begins. You train the AI model, and finally you deploy it out into the real world. Let's start right at the beginning with the absolute foundation of it all, the data. Think about it. Any intelligence, whether it's human or artificial, has to learn from something. For an AI, its entire education comes from data. You can think of this data as its textbook. And just like with any student, the quality of that textbook is going to determine how much it can actually learn. So, for a pneumonia detector, the textbook is a massive collection of hospital chest x-rays. But here's the catch. The images by themselves are totally useless. The real secret sauce is the labeling. This is where human experts, in this case radiologists, go through every single scan and tag it normal or pneumonia. Those little labels are what turn a bunch of meaningless pixels into powerful lessons for AI. So just to be super clear, labeled data is simply information a human has given context to. It's basically like creating flashcards for AI. You show it an image of lungs and say this is normal. You show it another with cloudy spots and say this is pneumonia. Without labels, they're just pictures with them. They become the bedrock of the AI's knowledge. But here's the thing about raw data from the real world. It's almost always messy, so just like you'd proofread a textbook before handing it to a student, the data needs to be cleaned and standardized. We're talking about getting rid of blurry images, making sure all the scans are aligned the same way, normalizing brightness. This pre-processing is absolutely vital because you want the AI to focus on the real patterns of the disease, not get confused by random noise. Alright, so we've got our clean, perfectly labeled textbook. Now it's time for the AI to actually go to school. This is the training phase, and this is where the real learning finally begins. But you wouldn't give a student the answer key to the final exam on the first day, right? Of course not. So before training even starts, all that data gets split into 3 separate piles. The biggest chunk, the training set, is for the day-to-day learning. A smaller validation set is used for little pop quizzes to check its progress, and the last part, the test set, gets locked away in a vault, completely untouched until the final exam. And this separation is non-negotiable. It's incredibly important. The goal isn't to create an AI that just memorizes the training images like a parrot. We need it to genuinely understand the underlying patterns of pneumonia. By keeping that test data completely separate, we can be sure we are evaluating its real-world knowledge, not just its ability to cram for a test. Now here's something most people never see. During training, the model keeps checking its performance on that validation set. If it starts getting better on the training data but worse on validation data, that's a warning sign called overfitting. It means the AI is memorizing instead of truly learning. Those validation checks help us stop training at the perfect moment, right before things go wrong. And here's another behind-the-scenes layer: hyperparameter tuning. This is where we fine-tune the rules of how the AI learns. Things like how fast it should learn, how many images it sees at once, how deep its neural network should be. These tweaks might sound small, but they massively affect how well the model performs. So what's the actual brain doing all this learning? Well, it's a special kind of AI model called a convolutional neural network, or CNN for short. The easiest way to think about it is as a system inspired by how the human visual cortex works. It learns to recognize simple things first, textures, and then builds that up to understand far more complex patterns, including the subtle signs of disease. During training, CNN looks at thousands and thousands of these labeled X-rays over and over again. For each one, it makes a guess, pneumonia or normal. Then it checks its answer against the real label and, if it's wrong, makes a tiny adjustment to its internal wiring. Repeat this millions of times, and those tiny adjustments add up until it becomes incredibly good at spotting the patterns it's looking for. After all that training and studying, it's time to see what our AI has really learned. This is the final exam, the moment of truth where it must prove it can solve problems which it has never encountered before. This is when we unlock that vault and bring out the test set. Its performance on these fresh, unseen images is the single truest measure of its ability. This isn't a practice run, this is our best prediction of how it will perform in a real hospital. And we don't just give it a simple pass or fail, we measure its performance with very specific metrics. Accuracy, how often is it right? I mean overall accuracy. Precision, when it says pneumonia, is it correct? Recall, of all real pneumonia cases, how many did it catch? Together, these give us a detailed report card on the AI. Now, assuming the AI passes its exams with flying colors, it's ready to graduate from the research lab and begin its career in the clinic. But before that, there's one final behind-the-scenes step: model exporting and optimization. We need to convert the heavy model into a lightweight, fast format, like ONNX or TensorRT, so it can run instantly on real hospital systems. Think of it like taking a huge textbook and turning it into a pocket guide the doctor can use in seconds. Now finally, the AI, which is optimized tools, is ready for deployment. Now that we have a sense of how it learns, let's check out what computer vision can actually do. And it's not just one single trick. It's really a whole toolbox filled with amazing capabilities. Okay, let's start with an important distinction: object detection versus image segmentation. So, with object detection, the AI draws a simple box around something and says, hey, there's a bicycle in this box. But image segmentation, that goes a huge step further. It outlines the exact pixel-perfect shape of the object. And that level of detail is absolutely critical for things like, say, defining the precise boundary of a tumor in a medical scan, or for a self-driving car to know the exact shape of a pedestrian it needs to avoid. Next up is a capability that I bet a lot of us use without even realizing it: optical character recognition, or OCR. This is basically how we teach computers to read text right out of images, and totally changing how banking and healthcare are handling paperwork. And this technology is just everywhere. OCR is what lets you point your phone's camera at a menu in another language and get an instant translation. It's also the powerhouse behind digitizing mountains of old paper records, completely automating data entry, and saving just countless hours of boring manual work. Of course, we have to talk about facial recognition. This is probably the most well-known and sometimes controversial application of computer vision. The system is trained to identify or verify a person based on their unique facial features. And you really do see it everywhere. It's what unlocks your smartphone 100 times a day. It's used for secure biometric login on your banking apps. And it's what's helping to speed you through some of those security lines at the airport. It all works by mapping the unique geometry of a face. Things like the distance between your eyes or the shape of your chin. And hey, if these videos help you understand AI better, make sure to subscribe so you don't miss any upcoming deep dives. So, when you start to put all these different capabilities together, you begin to see how computer vision isn't just a cool tech demo. It's fundamentally changing entire industries. I mean, in healthcare, the impact is huge. It goes way beyond just flagging pneumonia. We're talking about systems that can precisely outline tumors for radiation therapy and even give surgeons real-time guidance and data during incredibly complex operations. In transportation, it's obviously the core technology that makes self-driving cars possible, but it's also used to manage traffic flow in smart cities, optimizing stoplights to reduce congestion. And get this, NASA has even used it to help spacecraft land safely on other planets by identifying and avoiding dangerous rocks and craters. How cool is that? And then you have retail and manufacturing, where it's a total game changer. It's the engine behind those cashierless stores where you can just walk out. It powers those virtual try-on apps that let you see how clothes look on you. And on the factory floor, it's tirelessly inspecting products on an assembly line, spotting tiny defects with superhuman speed and accuracy. In agriculture, drones fly over fields, monitoring crop health from the sky. And of course, it brings us full circle back to healthcare, where these systems are assisting doctors with the very same complex medical scans we started with. All of this stuff feels incredibly futuristic, almost like something out of a sci-fi movie. But the truth is, this overnight revolution has actually been decades in the making. So let's take a quick trip back in time and see how we got here. The story really starts way back in the 1960s, with scientists studying how a cat's brain responds to simple lines and edges. Super foundational work. Then fast forward to 1982, when a guy named David Marr laid out a groundbreaking theory of how vision works. But the huge leaps came much later. In 2009, we got the ImageNet dataset arrived, which is a total game changer, giving researchers millions of labeled images to train their systems on. And then came 2012. A neural network called Alex-Net used that data and shocked the world. It didn't just win a competition, it proved deep learning could slash error rates and achieve accuracy levels nobody thought were possible. That breakthrough kicked off the entire AI boom we're living in today. And that brings us right back to now. This technology is already amazing, but you know what? It's still evolving so rapidly. So the big question is, where is this all headed? Well, there are three huge trends shaping the future. First, there's Edge AI. This is all about doing the processing right on the device itself, like in a self-driving car, instead of sending data to the cloud. It's way faster and much more private. Second is multimodal AI, which is about combining vision with other senses like language and audio to build a much richer, more context-aware understanding of the world. And finally, there's a massive push for ethical and explainable AI, developing systems where we can actually understand why they made a certain decision, making them more transparent and less biased. And that brings us to our final thought for today. The power of computer vision is just undeniable. We are giving machines a sense that until now it was purely biological, and the companies with this ability are going to lead industries. But with this incredible new power comes profound responsibility. So the question we're all left with isn't just about what machines can see anymore. It's about what we as a society decide they should be allowed to see. Thanks for watching UTC AI Studio. AI powered, creativity fueled. I'll see you in the next video, where we explore what is reinforcement learning. Till then, as always, keep learning, keep building, and keep creating with AI.